Hello everyone. Last lecture, we were doing queuing system with bulk service. In this problem, the server is able to serve two customers at the same time. So we defined the states as 0 prime, 0, and 1, 2, 3, and so on, which is n for n greater than equal to 1. 0 prime was none in service, 0 was server is busy, none waiting, and n is n waiting. We set up a transition Any questions for this? Then we wrote the balance equations and gave the solution for the balance equations. That solution was phi n is alpha n lambda 1 minus alpha over lambda plus mu 1 minus alpha for n greater than equal to 0. Here alpha was root 1 plus lambda mu minus 1 by 2, and by 0 prime was mu 1 minus alpha over lambda minus mu 1 minus alpha. So after doing that, we were calculating the matrix. So we were calculating LQ. So since the problem setup of the definition of the states, in 0 prime, no one is in the queue. In 0, no one is in the queue. And in n people are in the queue. So the number of people in the queue will come out as summation n times pi n, n equal to 1 to infinity. We have the expression of pi n from the previous page. So we substitute that. It is lambda 1 minus alpha over lambda plus mu 1 minus alpha. This part is independent of n. And then we had n times the remaining thing is alpha to the n. So to see this, let's go back on pi n. This is the only term alpha n that is dependent on n, so that remains in the summation. Everything else comes outside. Is that clear? Any questions on this? Any questions? Comments? So, what is summation n alpha n? We did that in the previous lectures when we were doing MM1s. Anybody remember that? What is summation n alpha n? This is given as alpha 1 plus alpha square. So we substitute this 1 over alpha will cancel here with one of them. So we can have the overall expression LQ is lambda alpha on 1 minus alpha. So, so I have calculated LQ. What is WQ? Using Little's law. We calculated LQ. How do we calculate WQ? Any guesses? Given LQ, calculate WQ.
Is it LQ by lane?
Yeah, exactly right. Both of you are correct. It's just LQ by lambda. So just the lambda goes away. Great. So we have now calculated WQ. How do I calculate W? WQ, how do I get W? You know the waiting time in the queue? What is the overall time in the system? Waiting time in the queue plus the service time. How much is the service time?
1/mu.
Yes, part over me. And now to get with L using Little's law, how would I get that? What is L from W using Little's law?
And the read.
Lambda. So this is an approach with which you can calculate all the metrics even for bulk analysis. So now what we have seen is we saw the bulk and death processes, we saw queuing theory as a special case of it. We studied the um, MM1 system, general MMC system. We saw the limited capacity. We saw when MM1 or MM2 is better, which is generalizable to any number of servers. We calculated the LW, LQ, WQ metrics for all the MMC, MMS type systems. We went over also the bulk arrivals, sorry, bulk departures to see what happens if elevator ecosystem can serve multiple customers at the same time. So the next topic we will go over briefly is what happens when the service is not memoryless. So we are considering MG1 system. So in MG1 system, the first M is the arrivals. So the arrivals process is still a memoryless process, which means that the arrivals come at a Poisson process with a rate of lambda. This is the service process. So the service process, we are considering that it is not exponential. It is any general distribution with the mean service time expected value of S, which for exponential was 1 upon mu, and variance V of S. So this is mean service time, this is variance of service time. For exponential, I think variance is 1 over mu square. Second moment was 2 upon mu square, so variance became mu square. And this one means there is only one server. Any questions in the notations? If we have mg1 system, then there is a formula which is, let's check formula, which basically gives LQ as rho square plus lambda square V is divided by rho times 1 plus rho, where rho equal to lambda times expected value. So in the exponential case, this was lambda upon mu because expected value of service time was 1 upon mu. So in general for mg1, rho is given by lambda times E of s, and LQ formula is given as rho square plus lambda square variance of service time divided by y. Any questions about this one? Now we are taking special cases of this formula, and we will consider two setups where the service time is deterministic and where it is exponential. Which one do you think will have larger length in the queue? If the service is deterministic or the service is exponential? Which will have larger LQ? So let us consider that. Let us consider a MD1 system. D means deterministic. In this setup, when we are comparing, we have to keep something constant. So we will assume expected value of service time is same in both. Lambda is same in both. So rho, which is the occupancy measure, is same in both the setups. Okay. So for the deterministic setup, we have variance of the service time will be 0. You substitute in the previous formula LQ, when the variance is 0, the second term in the numerator is 0, it becomes rho square 1 twice. Any questions on this calculation? Let's consider MN1. You can already see from the expression here, MM1 will be larger because we will have the second term. In the first case, we did not have the second term. So for MM1, we have variance of service time is 1 upon mu square. So LQ is rho square plus lambda square. Variance is 1 over mu square over twice 1 times rho. Now lambda upon mu is rho, so lambda square upon mu square is also rho square. Rho square plus rho square is 2 rho square. 2 cancels out, so this is rho square upon 1 plus rho. The calculation's clear. So what you see essentially is that the length of people in the queue, or the number of people waiting in the queue, is double in the case of MM1 system as compared to MD1 system. So MD1 system will have half the length of the queue. So what we typically say is, if both service and arrivals were deterministic, then the length of the queue will be zero. If you have um, arrivals at a lower rate than departures. So if departures are faster, then there will be no queue if both arrival and departure were deterministic. What that essentially means is, um, if we have the overall length in the queue, length of the queue as rho square over 1 minus rho, half of that is attributed to the service being memoryless versus deterministic, and the other half is attributed to the arrivals being memoryless or deterministic. Does that make sense? So we have calculated LQ. All of the metrics are calculated the same. WQ is LQ by lambda. W is WQ plus expected value of service time. And L is, since service is not exponential, the 1 over Q is changed with expected value of service time. Other than that, all the formulas kind of remain the same. Any questions?
So the formulas you have right now up on the screen, those formulas always hold up regardless of the case, correct?
These hold for any MG1 system.
For any, but just like the fact that WQ equals LQ over lambda, for example.
Yeah, that happens whenever you do not need any queue construction. So basically lambda A equal to lambda, and people arrive one at a time. So as long as those things happen, those formulas are always valid.
Okay, when lambda equals lambda A, then you can
Yes,
always apply these laws,
yes,
basically.
yeah,
Gotcha.
and the customers arriving one at a time. So basically no correlation. So which we have here, memoryless process.
No, no quarrel. Oh, it depends on the arrival being
This
memoryless as
depends.
well.
Yes, yes. This depends on arrival being one at a time. So no bulk arrivals. In the case of
Gotcha.
bulk arrivals, these formulas, the Litter's law do not hold. That's generally.
Thank you for clarifying.
Any other questions or thoughts? We are finishing the chapter on queue theory with this. Right. If there are no questions, then let's go over to the next chapter. This is network of queues. So, network of queue. So far, we basically did a single queue. So people were coming in and going out of a queue. But many of the systems have more complex type of systems. Arrival comes in, go to a server, let's say server one, and then goes to a server, and then goes. There could be other type of system where you can say that with probability p it goes to server 2, with probability 1 minus p it again goes back to server. So you can have connections inside. So we classify network of queues in two categories. One is open system, and other is closed system. Open system is where there are external arrivals. There has to be external arrivals to the system. Most days, everything remains inside. They just keep cycling between the different servers and never exit. So this is no external arrivals. For the purpose of this course, we will only be working at open queuing systems. So let us understand one example. So we have incoming, go to server 1, and after the departure from server 1, go to server 2, and then exit. So there is a queue here, and then there is a queue here. So what is happening is you enter the queue of the server 1, and the consider both the server ones are like MM1 systems. So you have a queue build up, the top of the queue goes to the server, and then after serving enters the queue of the second server. From the queue, the head goes to server 2 and exits the system. Is this example clear? This is called a tandem or sequential system. So let us say arrival rate of customers here is lambda. The service rate of server 1 is mu1, and the service rate of server 2 is mu2. So assuming that everything is memoryless, which means the arrival and the services are memoryless processes, which means exponential and Poisson, it can be shown that the departure process from here is actually also a memoryless process. So the process here of basically the people that are exiting server 1 is a Poisson process. Now the question that we are asking is, what is the rate of arrival of customers at server 2? Rate of arrival of customers at server. Guesses. is driver itself. Is the problem setup clear?
Is it actually mu1?
Why?
Can we assume that as soon as they're done with server one, they start server two?
Yes, that's what happens.
Okay, then yeah, then that makes sense. You don't even, yeah, I mean, maybe in a practical setting, there would be like you have to walk over to the next server or something, but
Okay, all right, that's a great answer. Um, any other thoughts by anyone? Anybody else thinks that it is not mu1? Okay, let me ask this way. Um, Suppose people go into Starbucks and after leaving Starbucks, immediately go to no, let's switch them. Go to first, let's say, an eating place, let's say Subway. So go to eating place like Subway, and then go to Starbucks after lunch. Now, people are coming at the rate of 1,000 customers per hour into the first shop. Okay, the first shop serves everyone in, so 1,000 people are coming at the rate of in 1 hour at the shop. Okay, the first shop basically processes them instantaneously, more or less instantaneously. Like mu is very very large. Okay, so if the first shop processes them instantaneously, which means mu is close to zero, or yeah, mu is close to zero, mu1 is close to zero, then people coming in the second shop, what will be the rate of people coming into the second shop? 1,000 people per hour were entering the first shop. First shop processes them near instantaneously. Would you have infinite arrival rate at the second shop?
No,
Right. So what would it be?
we lambda.
It will be lambda, yes. If 1,000 people per hour are coming at shop one and shop one is stable, then again 1,000 customers per hour will enter second shop. It does not matter what mu one is, as long as the system is stable, which means as long as mu one is greater than lambda. The answer is just lambda. It's not. It has nothing to do with the service rate, assuming stability. Any
So to
question?
repeat, you said it's lambda as long as lambda, sorry, as long as mu is greater than lambda or lambda is greater than mu.
The service rate has to be bigger, right? So mu one and mu two to be both larger than. Any questions about this? This is probably the hardest concept in this lecture.
Part of this is due to the fact that it's memoryless, right?
Yes. Yes, because of memoryless, even the departure process becomes memoryless. Otherwise, not.
So this is actually in terms of that notation, it would be M
Tandem MM1 system.
tandem MM1 system. Okay. That's how you say it. That's how you write it.
Yes.
Gotcha. Okay. Tandem MM1. Why not tandem MM2?
Both the systems are MM1.
Oh, it's two. It's two MM1 systems beside each other.
Yes, two MM1 systems in tandem or in sequence.
Okay. So if it was like a two MM2 systems beside each other, there would actually just be servers at each
Yes.
location.
Yes, there will be two servers at each location.
Gotcha. Perfect.
Alright. So let us see how to analyze it. The first approach of making the the balance equations and everything is doable. The stage you will use is n comma m, which is n customers at server 1 and m customers at server 2. You can write n comma m and write down their balance equations. Even though all this is writable, the the system becomes very complex because it's infinite system. We can't directly solve it, so we'll use another approach to solve this type of system. So we already did pi n for mm1, so which was probability that there are n customers at server 1. That is the formula of pi n for server 1. So pi n for mm1 was already given to us from the previous chapter, which was lambda over mu power n times 1 minus lambda mu. Similarly, probability that there are n customers at server 2 is pi m for mm1, which is lambda upon mu m1 minus lambda. Now these expressions actually these are directly coming from mm1, the formula for pi n. Assuming that is clear, for a tandem queue, pi n comma m, which is probability that there are n customers in system 1 and n customers in system 2, is just the product of these two. Lambda over mu 1 and 1 is mu 1. So it's basically behaving as if the two servers are independent. Because pi n comma m is probability of n customers at server 1 times m customers at server. That is basically how independence works, that joint probability is product of the marginal probabilities.
I apologize, Professor. I'm not following the notation. Do we multiply the two?
Yes, everything is multiplied.
Thank you.
Mhm. So with that in mind, what is the um, average number of customers in the system? Any thoughts? How will we calculate average number of customers in the system? Many approaches, you can basically do it summation of n plus m by n m over all n and m. Since this is product, it will actually simplify. This is once you solve this, this is lambda over mu1 minus lambda plus lambda over mu2 minus lambda, which is the average number of customers in the first server plus the average number of customers in the second server. So the average number of customers actually just sums over the two servers. This was the formula from MM1, which is the average number of customers in server 1. This is again from MM1 formula, which gives you the average number of customers in system 2. Any questions here? Next question. What is W? L upon using Little's law. What would the arrival rate be? That's the arrival rate of customers. So lambda is the arrival rate here, lambda is the arrival rate here. Should we use lambda or 2 lambda? We are only talking about the waiting time of a customer who enters here. So we are only talking about external arrivals. So the arrival rate we consider is only that of the new arrivals, which is lambda. This is given as mu1 minus lambda plus 1 over mu minus lambda. And that makes sense because it is waiting time from the first system plus waiting time from the second system. Any questions for this expressions? So by these you can basically see all the LW, LQ, WQ are just the sum of the corresponding expressions for the first plus that for the second. Any questions? Let's not generalize this setup. So we consider K servers. So at server I, we have external arrival rate. Is independent person process. Three R T. The arrival joined in to server I. Joins the queue at server I until turn for service. Once customer is served by server I, the customer joins queue in front server J. The probability that J. We summation of J over J, P by J equals 1. Sorry, not equal to 1. Less than. And 1 minus summation J equal to 1. K P I J is the probability customer departs. Is this setup clear or we need some examples to understand it?
An example would be nice.
Sure. So let us consider 3 servers. That's server 1, server 2, and server 3. So the first statement says there is an arrival rate of a process R1 here, R2 here, and R3 here. And after completing the service, let us say customer goes to this server with probability 1/4. Customer goes here with probability 1/4 and departs with probability half. From server 2, let us say the customer just goes to server 3 with probability. From server 3 with probability half enters the queue of server 1 and with probability half, it departs the system. So in this case, probability from the first server, the PIJs, so probability from the first server to the second one is 1/4. P13 is 1/4. P23 is 1. P31 is 1. Rest are zeros. It can also go to itself. So 3 could also go back to 3 with certain probability. Does this setup make sense? So let's consider our previous tandem system. So we had server 1, then server 2, lambda. So in this case, the arrival rate at the first was lambda. Arrival rate at the second was 0. Then probability from 1 to 2 was 1. Probability from 1 to 1 was 0. Probability from 2 to 1 and probability from 2 to 2 were both zeros. We will be starting with format. So the previous setup is then a generalization of uh, this tandem system. So now, first thing we have to see is, for a system like this, what is the overall arrival rate at the first server? It's not just R1. At the first servers, people come in from external, as well as in this case, the people that are coming from server 3 with probability 1/2. So let us consider this example and see how are we going to find the arrival rates at different servers. So that's the first key step. How do I find all these arrival rates? Okay. So let us say overall arrival rate. Let's first consider this example and then we can generalize. Servers, let us say, are lambda1, lambda2, and lambda3, which we don't know. The question only gives ours. In this example, the arrival rate at server 1 is there is a R1, which is the arrival rate here. Okay. Then half of the arrivals at server 3. How much are the arrivals at server 3? Arrivals at server 1 is R1 plus half of the arrivals of server 3. What is arrivals at server 3? Is it R3 or lambda 3? Okay, so in this case, lambda is R1 plus half of arrivals at server 3. How much is the arrivals at server 3? It's lambda 3. Because lambda 3 is the total number of arrivals that happen at server 3. So with that intuition, how do we write the equation for server 2? The arrivals at server 2 come from external as well as with 1/4 the arrivals of server 1. Okay. So what is the overall arrivals at server 2? R2 plus 1/4 what?
Lambda 1.
Lambda. Yes. Lambda 2 is 2 plus 1. Then let's see what is lambda 3 equals. Lambda 3 is you have external R3, then with probability 1 from server 2. So 1 plus the arrival rate at server 2 plus 1/4 from server 1. So this is R3 plus with probability 1 from server 2, that is plus lambda 2 and with 1/4 probability from lambda 1. Is that clear? So three equations, three variables. Solve lambda 1, lambda. Does the methodology make sense? So
Will
given
we be
this,
given R1, R2, and R3?
yes, you should be given all the R's, you should be given all the PIJs and the service rates, which are mu1, mu2, mu3. So we are assuming R's, PIJs, and mu's. But lambdas are not, so lambdas had to be found. So having found the lambdas, we can ask the same type of questions as we did for the tandem queue. First is, what is the probability that there are n customers at server J? And that is nothing but lambda j is the arrival rate, mu j is the service rate, over n, 1 minus lambda j. We did the independence result among the servers that holds even in this type of system. So if somebody says what is the probability of n1 server sets, n1 customers at server 1, n2 customers at server 2, to nk customers at server k, that is the product lambda j, mu j, nj, alpha j. Just get it done, which means everything is independent. So LW formulas should follow the same way. So just need that. L is total number of customers in the system. Sum of customers at server j, lambda j, upon mu j minus lambda j. This is the total number of customers in the system. There is an interesting next part. What is W? Is L upon something. What is that something? W is average time customer spends in the system. How would we calculate this? In little slow, what would be the denominator? Think of in the tandem system we use lambda, not 2 lambda. So in this setup, what would it be? Any thoughts? It's summation j equal to 1 to k. Is it lambda j or rj? It will only be external arrivals because we are talking about the waiting time of a external arrival of a customer. So W is given as L divided by summation of Rj. So this is basically how you can calculate L and W for a open queuing system. So we gave these equations for only an example, the lambdas. We can now write it for general system. For general system, we'll just have lambda j, which are the arrivals at server j, is the external arrivals rj, plus the sum of I equals 1 to k. Lambda I is the arrival at server I with probability Pij you enter server j. So this equation you have for all I from 1 to k. These are k equations k variables solve. Is this clear? Any questions on this?
So if everything except for R1, like R2, R3, R4, excuse me, etc., if all of those were zero, that would just mean that there's only one flow into the first server and then it just goes through the rest of the system.
Yes, it's like the tandem where the arrivals were only at the first server.
Gotcha. Okay. Because in this example, there was external arrivals to like server 2, even though they didn't go to server 1, for example.
Yes, so any of the r's could be zero, just that the sum over r has to be positive, right? Because there has to be some external arrivals.
Yes, yes. Okay. You need some external arrivals at some point in the system. But it
Yes,
doesn't matter. It doesn't matter where.
it doesn't matter where because the names of servers were arbitrary, they could be renamed.
Gotcha. These are all MM1 processes.
Yes, we could have, yeah, we could have called the first server as server 2 and second as server 1, doesn't matter.
Right. Hmm. Okay.
So the extension basically takes care of all these type of possibilities. So it's actually a very general process. So let's read it again. At server I, you have an external arrival at the rate of Ri. You join the queue until your turn for service. Once you are served by server I, you go to server J with probability Pij. And with probability 1 minus summation Pij, you depart. And that's the generality of the system, which is an open system where you can have external arrivals as well as go between the queues. So in closed system, as I mentioned, there are no external arrivals or departures. So those are mainly used in some chemical processes. Since I do not know much more applications of closed systems, open systems, we can easily imagine the applications. So that's why in this course we just focused on open systems. Open systems are easy to understand because you will go to one server and then you can go to other shops with certain probability. For example, you go into a Starbucks and then you can say with certain probability I go to Grey House, certain probability I go to Starbucks or something of that nature, and you can set up an open system of people going through different shops or different type of things. Or you are going into a airport line with certain probability you might be asked to go to another counter, and you can be basically going across different type of queues. So that is how these open type of systems are useful in practice. and the analysis is not very hard. The hardest thing that we learned pretty much was that in this network of queues, the arrival at the second server here, which is that the rate of arrival is lambda and it is not dependent on mu as long as system is stable. And that was something that we used even in the network of queues, where we basically um, took into account that the servers outgoing from a server will be the same rate as lambda, not based on the service rate. So when we set up the simultaneous equations, we basically did half time Pij times the arrival rate of the server, not the departure rate of the server. The service rate. So departure rate and arrival rate are the same, but the service rate is different. And that is, I think, one of the key concept to understand. Other than that, we basically use this setup to understand this. So we are more or less done with this chapter. We can do one more example for this open system, and that finishes the main part of the course. In the next lectures, we'll mainly go over some extension to Markov decision processes, which is reinforcement learning introduction. And other than Markov decision processes and doing the homework discussions, we are pretty much done with the course. So yeah, unless we do something very meaningful in reinforcement learning, this will be pretty much most of the contents for us.
So then, in terms of content on the third exam, it will be
till today.
just through today. Okay, so it'd be queuing systems, MM1 systems, all of that.
Birth and death processes.
Yes, also
some
that.
part of to understand Markov chain that we did later.
Gotcha. Okay.
Okay, talk to you on Thursday. Thanks, everyone.
Thank you. Thank you.
Thank you, Professor. Do you know, is there an average for the midterms too?
Midterm 2 has not been graded yet, so I think it will be still a week.
It actually just got posted.
Okay, then I haven't looked at it. I need to see it.
That's okay. Thank you.
Thank you.
Thank you.